All right, let's pull back the curtain on one of the CPU's oldest and, honestly, most clever tricks. We're talking about shift instructions, the crazy fast way your computer moves data around at its most basic level. So think about this for a second. Deep down, a processor only gets binary, right? Ones and zeros. So how in the world does it do something like multiplication or division without getting totally bogged down? It's not like it can just whip out a calculator.
Well, the answer is kind of beautiful in its simplicity. Instead of doing a bunch of heavy math, they just shuffle the bits. They slide the ones and zeros to the left or to the right. It's called bit shifting, and believe me, it's a massive deal in low-level computing. Okay, so here's our game plan. We're going to start with the most basic shift, then see how things change when negative numbers show up, check out a way to shift without losing any data, and even get into a real pro-level move before we wrap it all up. First up, let's talk about the granddaddy of them all, the instruction that really started this whole thing, the logical shift. The rule here is super simple. Just imagine you've got a line of bits sitting in a CPU register. A logical shift just slides every single bit one spot over. And that empty space that opens up, it just gets filled with a zero. That's it. That's the whole rule. Let's actually see this happen with a logical shift left. Okay, so look. In step 1, that bit on the far left, we call it the most significant bit. It gets pushed out. See you later. It's just gone. Then in step 2, everybody else shuffles down one spot to the left. And finally, step 3, a brand new 0 pops into that empty space that just opened up on the far right. So why does this matter? Well, look at the number we ended up with. We started with 10, and now we have 0010100, which is 20. We just multiplied by 2 without doing any actual multiplication. We just slid some bits around. For a CPU, that is ridiculously fast and efficient. And as you've probably guessed, this whole thing works in reverse too. With a logical shift right, the bit on the far right gets tossed out, everything slides over to the right, and a 0 gets added to that new empty spot on the left. And boom, there it is, the flip side. When we shift our original number 10 to the right, we get 0000101, which is the binary for 5. We just performed integer division by 2. This is the CPU's ultimate shortcut for quick and dirty multiplication and division. All right, let's move on, because so far, so good, right? But we've only been talking about positive numbers. Things get a little more complicated when you throw negative numbers into the mix. So here's the problem. In most systems, that very first bit on the left is the sign bit. A 1 means it's a negative number. Now, if we do our normal logical shift right and just blindly stick a 0 in the front, we could accidentally change a negative number into a positive one, and that would completely corrupt our data. Not good. To fix this, the folks who design processors came up with something called the arithmetic shift. Its one and only job is to perform a shift while making absolutely sure the sign of the number doesn't change. Okay, let's look at arithmetic shift right. The first 2 steps, exactly the same. The rightmost bit gets kicked out and everyone shuffles over. But here's where the magic happens. Step 3. Instead of inserting a 0, we take a copy of the original sign bit and put that in the empty space. So if it was negative, it stays negative. This preserves the sign perfectly. This comparison really makes it crystal clear, doesn't it? It all comes down to what fills that empty spot. The logical shift is simple, but it's totally blind to the sign. It just always uses a 0. The arithmetic shift is smarter. It knows to look at the original sign bit and copy it, keeping the number's integrity intact. And here's a little fun fact that makes life way easier for the people who design these chips. When you're shifting to the left, it turns out there's no difference at all between logical and arithmetic. The math just works out, so you can use the exact same operation whether the number is signed or unsigned. Pretty neat, huh? So up to this point, every time we do a shift, we're throwing a bit away. But what if that bit is important? What if you need to shuffle things around without losing any information at all? Well, that's where the rotate instruction comes into play. It's a fantastic idea. Instead of just tossing that bit into the void, it recycles it. The bit that falls off one end just wraps all the way around and fills the empty space at the other end. It's basically a circular shift. So here's how a rotate right works. All the bits shuffle to the right, just like we've seen before. But that one bit that gets pushed out from the right side, it doesn't disappear. It takes a journey all the way around to the other side and slots itself right into the empty space on the left. No data lost, just rearranged.
Okay, now we're getting into the pro-level stuff. For our final, most advanced type of shift, we have to talk about a special little 1-bit storage spot in the CPU called the carry flag. So a rotate with carry is like a regular rotation, but with an extra player on the field. If you have an 8-bit number, this becomes a 9-bit rotation. The bit that shifts out of your number goes into the carry flag, and whatever was already in the carry flag moves into the empty space in your number. This is a super powerful tool for doing math on numbers that are too big to fit in a single register.
Okay, we have covered a lot of ground. I know. So let's bring it all home and just boil it down to the key rules for each type of shift we talked about. This table right here, this is your ultimate cheat sheet. It really all comes down to 2 simple questions. What happens to the bit that gets pushed out, and what fills the empty space? For logical, the bit's discarded and a 0 comes in. For arithmetic, right, it's discarded and a copy of the sign bit comes in. For rotate, the outgoing bit itself just loops around. And for rotate with carry, the carry flag gets in on the action. And that's really the main idea to walk away with. All the incredible things our computers do, from rendering amazing graphics in games to complex scientific modeling, it's all built on a foundation of ridiculously simple, blazing fast operations, just like these. It all starts with shuffling some bits. So I'll leave you with this question to chew on. We've just seen how a simple little shuffle can take the place of complex math. So what other big, hairy problems in computing are actually being solved by surprisingly simple, elegant little tricks, right down at the hardware level? Thanks for digging into this with me.